it's a fancy title, but I'm going to talk about a couple of things. One is particularly homegrown project here at IIT Gandhinagar, which we are trying to look at NVMs in smartphones, and the 75% of the second half is essentially something on storage that I did when I was in the industry. So it'll give you a flavor as to where the storage industry is moving, especially from architecture and a software or OS perspective. All right, so this is a cartoon that I really like in terms of just explaining why persistent memory is actually becoming important. So if you look at this, on the x-axis you have the kind of bandwidth that a particular type of memory technology can provide, and on the latency, on the y-axis is the corresponding latency that particular memory technology can provide. So at the top, or the top left end, is essentially the hard disk drives, which are super slow. They also give you the least amount of latency, but this graph in some sense is also a measure of dollar per bit. So the more on the left you are, the cheaper kind of a technology it is, so you can have a lot of it. The more to the right you go, the costlier the technology becomes, so you can have a very small fraction of it, right? So essentially in any modern computer system you would see a combination of 2 or 3 of these things to form a complete storage / memory system. Before persistent memory came into being, there was this huge gap between where NAND flash was and where DRAM was. So this is the gap that persistent memory is trying to fill, and in the first half of the talk what I'm going to look at is how the technologies that fit in this domain can be used to develop memory hierarchies for handheld devices, right? So one of the other things that is good with things that fall in that particular rectangle over there is essentially things like technologies like PCM fall in that bracket, which have the additional benefit of scaling very well. So depending on who you ask, DRAM is supposed to be dead around 40 nanometers, but still going strong. The good thing about PCM or other persistent memories is the fact that they can scale very well. So they can go up to 5 or 7 nanometers. So essentially that gives you a lot of capacity scaling for free, just because the process technology scales very well. They have very good power characteristics. Unlike DRAM, these things don't need to be refreshed at all. They, as was mentioned in a whole bunch of other presentations before, they have this drawback of having higher read latencies and higher write latencies, and depending on which sort of publication you're referring to, it's either closer to DRAM or closer to flash, right? But one of the things that probably has not been mentioned yet is the fact that these PCM sort of systems, what they also provide you is this additional capacity. So given a particular area, particular millimeter square, the amount of bits that you can pack in X millimeter square of PCM is approximately 2 to 4 times higher than what you can pack in the same millimeter square for the DRAM technology. So the capacity requirements are something that are handled decently well by things that fall in the persistent memory domain, and that's why they sort of tend to be a very attractive alternative for replacing DRAM at certain point in time. All right, the couple of the things that I'm not going to talk about but are essentially important while sort of trying to look at these persistent memories is essentially this endurance factor as to how many write cycles you can have per bit, and for the time being we're just going to sort of ignore that. All right, so looking at the handheld domain, in the past 2 to 5 years, a lot of things have happened that have in terms of trends are very similar to what happened to servers probably 5 to 10 years ago, right? So if you look at the trend for high-end smartphones, the amount of main memory that these guys have is 6 GB today, right? And as and when things become much more complicated, this trend is going to go upwards with time. So 6 GB today, projections say it's going to be 8 to 10 gigabytes a couple of years from now. This essentially is probably 5 times or no, 12 times better than the first PC that I ever had. Anyways, the other thing that you have to take a note of, and this is essentially what this graph is showing. So if you look at this, the second bar over here and see that progression over time, and the third bar over there, and see the progression over time, which essentially shows the amount of memory. So that is gigabit per unit of DRAM that's going on over time. It's increasing over time for smartphones and top smartphones. So in 2015, the top line smartphone had around 5.7 gigabits per unit of DRAM, and the average smartphone had 3.62, and this is sort of growing exponentially, if you can see that. So capacity requirements are increasing, and that essentially means that the corresponding power requirements are also increasing, right? And one of the primary design constraints in smartphones is the fact that you need to have very good battery life. So you cannot have components that are keeping that are sort of taking up a whole lot of power just to sort of keep the data alive, right? So if you look at this particular projection over here, the amount of power that's consumed by memories is approximately 20%, and this was in 2014. So again, this trend is going to go over time, right? So again, the two trends that I'm trying to point out over here is, one, smartphones are going to need more and more capacity as time goes by, and the second thing is, if you keep to DRAM, if you stick with DRAM as your primary memory technologies, this fraction of the pie or the total amount of energy that's consumed in the system and that's consumed in memories is going to go up as well. So there has to be something done to sort of balance this equation, right? So if you look at a typical smartphone, and this is a very nice picture that I borrowed from this hexagon DSP paper that the Qualcomm guys had projected, and gives you a good idea as to how a traditional SoC sort of a traditional SoC in the smartphone domain differs from server-side CPU, right? So as you can see here, you have a whole bunch of these CPUs here, which share a last level cache. Then there is this on-chip interconnect, which is then connected to the LPDDR variant of DRAM over here. What you also see is there is this whole bunch of other things that are essentially utilizing the same memory controller over here as well. So this GPU is connected to the same memory controller. There are a couple of other DSPs and video and camera processing units that are utilizing this controller as well. So if you just look at this subsystem, it's very similar to what you would see in a traditional CPU, but if you look at the entire picture, it's somewhat a little different because there are additional components in there. So that's what makes the design of memory hierarchies for these sort of SoCs a little bit more interesting than in the case of traditional server architectures. All right, please feel free to stop me at any point in time if you have any questions. All right. Okay, so if I was to cartoonize this whole thing, this is what I would sort of come up with. I have a whole bunch of cores here, then there's a shared memory controller, and then these are the other units that are sort of sharing this controller as well. In the traditional case, what you usually have in contemporary SoCs is a couple of channels that are connected to an SODIMM, which is the LPDDR3 or the LPDDR4 sort of a variant, right? So this is what the situation looks like in your smartphone sort of today, right? Now, how do we sort of go from here and leverage the NVM technologies to create a memory hierarchy that has better power characteristics while at the same time not compromising anything on the user experience? Because as a user, what you want to do is essentially make your Facebook feed load as quickly as possible. Doesn't matter what kind of memory technology is there in your smartphone, right? So the user experience doesn't have to suffer. So that is the second constraint that we have to take care of, right? So what we did was essentially we analyzed a whole bunch of smartphone applications to figure out what the memory characteristics of these applications were. So there is this benchmark suit out of a university in China. It's called MobiSim. They have a bunch of applications that are representative of what people currently do with the smartphone. So there is a gaming app, there is something that is a browser, there is something that is a PDF reader, and it sort of simulates human behavior of moving things up and down, sort of scrolling through the whole thing, right? So what we wanted to take a look at is if I was to look at the behavior of memory in a typical smartphone, what would the axes sort of look like, right? So on the x-axis, we have sort of how time progresses, right? So this is just one application. Completely forgot what the name of this one is. But anyways, never mind, the insights pretty much remain constant. So if I go from left to right on the x-axis, this is the progression of time. So this is when sort of a game starts up and you are trying to, send the angry bird across the screen or something of that sort. On the y-axis are the different memory addresses that are being accessed by that particular application. So the interesting thing to note here is that doesn't matter what time or of your application you are looking at, there are certain regions of memory, this, and these three bands over here. These are the memory addresses that are actually being accessed the most, right? And there is some access in the rest of the region, but it's not a very concentrated access. Some addresses are accessed every once in a while. So the point here is that this sort of gave us the idea that, okay, well, these are the regions that are very heavily accessed. That essentially means the data that's sitting in them is probably latency critical as well, right? These are the regions that are not very heavily accessed. So the data in there is not latency critical. So how can we leverage this information to sort of feed back into our architectural analysis, right? And we did this sort of an analysis for a whole bunch of different applications, and it turns out almost all of them had very, very similar profiles, right? So there is this region of memory which is very lightly accessed, and there are regions of memory that are very heavily accessed. And again, you could argue that it is a function of how Android allocates its memory as well. And again, we're just looking at a stock version of Android and not trying to figure out or not trying to do anything fancy with how it's allocating memory. Anyways, so given what we have here is essentially now we are trying to use this information to design a memory hierarchy using NVMs to save on energy while not compromising user experience, right? So again, this is the whole insight. These are the four set of graphs that give us insight as to what can be done. And what we ended up doing here was essentially just doing a very simple thing where if you have X gigabytes of your total address space, you just chalk it up into multiple sub address spaces. As simple as that, right? If you have 4 gigabytes of space, you can probably chop it up into 2, 3, 4, 5, how many ever address spaces, and make each one of these address spaces controlled by one particular type of memory technology, right? So if in this particular example, I'm taking the entire address space, chunking it up into 3 different sort of sub address spaces, making the first one a DRAM space, the second one, for example, a PCM space, and the third one probably could be an STT-RAM sort of a space as well, right? Right. Yes, so the darkness is more access, yes, exactly. All right, so again, we leverage this insight to come up with a very simplistic architecture. And again, this is a very initial analysis and we are trying to work more towards this. But again, the initial analysis was, well, okay, rather than having a single memory controller as we had before, we have now 2 memory controllers, one for the DRAM, one for the NVM. And now if we have this, what are the effects of this sort of an architecture compared to what we had before on performance and user experience? And the initial results look very promising. Again, as I said before, you could probably take this up the memory space and chunk it up into more sort of address spaces as well, right? So these are the 2 configurations that we have sort of currently experimented with, and the results look very promising. So on the x-axis are different benchmarks. On the primary y-axis is normalized runtime for a particular application, and on the secondary y-axis is normalized memory energy. So again, I sort of have to confess that it's a not very good metric, but for the time being, for initial estimates, I think it's good enough. So what we ended up looking at were 4 different configurations, in which LL is the one which has both components, this one and this one, as the LPDDR space. So this is essentially your baseline. And with each successive one, we replace one of the regions with a PCM sort of a variant. So in this one, the first half is LPDDR, the second one is PCM. In this one, the first half is PCM, the second one is LPDDR. In this one, all is PCM, right? So again, if you go with all PCM, the results are pretty pessimistic. You ended up having a tremendous loss in user experience, which is a drop in performance. You can't have that. But again, that saves you the most energy as well. So that's one extreme. If you want to just go with energy savings and not care about user experience at all, you could go with all PCM. Again, not a good design point, but these are the 2 depending on which kind of a workload you're looking at and which sort of a memory region that particular workload is accessing. Turns out to be a better one. We did some experiments with 4 controllers as well. And again, don't look at the absolute numbers just yet. What I want to point you towards is sort of the relative insights. Yes.
You are not changing the address allocated by the underlying operating system.
No, not at all.
Just that, so that's the difference between an LP and a PL.
Yes, yes. All right. So again, initial results seems promising, and so again, I just wanted to get through this quickly because this is something that we started here, homegrown project, and I just wanted to sort of get the word out. And the idea here is that if you co-design well, I mean, what it points towards is that if you just naively replace something with something else, you get some benefits depending on what you place and where. But if I do the second level of optimization where I also say that, well, okay, I replace this region with PCM, but I also sort of go in and change the memory allocation of how Android places what data where, I could potentially have much better benefits in terms of energy savings as well as the drop in user experience, right? So the initial results, if I want to quote numbers, the best case drop in performance was around 3%, with I think a 2 controller and LP sort of a combination. Again, all right. So that was the first part of the talk, and I'm going to sort of context switch into storage part of it, which is something that I was really supposed to talk about. But again, I'll give you 5 seconds to sort of just context switch. The idea here is trying to look at data centers and how high-speed storage plays a vital role in how your user experience is affected from the data that you get from data centers, right? So if you look at data centers today, everything happens in these backend data centers that are either Google or Amazon or whatever you might have, right? So you type something in your smartphone into Google search, it actually goes to the backend, gets the HTML of your results, which is actually rendered on your phone or your web browser. And these humongous server farms essentially are running all kinds of applications there. That includes search, it includes analytics, things like your Google Drive, which just stores and archives data, is essentially somewhere down in the cloud. You don't exactly know where it is. And the other thing that you have to sort of care about, and I'll show how this sort of figures into all of this, is popular services like Facebook, right, have millions of users accessing the service at any given point in time. So if you look at the Facebook sort of access frequency graph, you'll see a huge uptick at 9 a.m. That's essentially when people get to their offices. The first thing they do is check their Facebook profiles. And then there is another huge uptick at around 5 p.m. when people are leaving and sort of saying buys for the day, right? Anyways, the point is there are these upticks in usage, and all these people who are designing these services have to sort of take into account that at any given point in time you could have, you know, these large upsurges, and none of the people who are essentially using that service at that point in time should feel that, okay, there are 50 million additional users that are signing into Facebook right now. That really shouldn't happen as far as you or me are concerned, right? Again, and with this whole buzz about IoT and sensors becoming cheaper by the day, you could have, or you are potentially going to have massive amounts of data that's coming in, and it's not going to come to your desktop. It's going to go to a server farm somewhere over there, where you'll actually go in and sort of try and derive some insights from that data. All right. So before I go any further, let me just quickly go through an example as to what an anatomy of so for example, a Google search kind of looks like, and that will help you sort of understand other stuff that I'm going to talk about later, right? So let's say you type, VOMS 2017 into your browser. What it eventually does is sort of packetizes the search query and sends it over to the data center of Google, where it's essentially received by web service front end, which essentially acts as sort of a decode engine. It's like, what is this? What kind of a service is being requested by this particular query? It's decoded. It tries to get the data that it needs from some sort of a caching layer. And again, this is essentially a cartoon representation of Google sort of a data center, and you could see there are multiple sort of tiers of servers that are doing various kinds of things. And all of these things have to sort of work in conjunction to give you your Google results, for example, right? So the request comes in, it tries to look up some sort of a caching server where the data that you might need is sitting in the DRAM of that particular server over there. For example, you don't find it in that caching tier, then you have to actually go in to the tier that services or that stores the data for the query that you're looking for. It looks it up, and there could potentially be multiple servers that have been distributed the job that actually you have to do. That particular query or data lookup or whatever that might be is executed on these multiple servers. The result is collated and sort of sent back to you. So the idea of this entire slide is that for that one Google search, right, there are multiple sort of servers that are kind of working in conjunction to make sure that you get your results as quickly as possible. And that's true for all the services that you can potentially think of that are essentially data center or web-based, right? All right, so when we are trying to sort of look at the performance of each one of these queries or each one of these Google searches, if you may, right? It boils down from the level of the data center, right, to the level of the individual server, which essentially looks something like this, right? So when you're looking at things at scale, when you're looking at these massive amounts of requests that have to be serviced in shorter windows of time, it's your stragglers who determine the performance of or your average performance rather, right? So if there are 10 servers that are working in conjunction to give you the data that you need, if 9 work in, let's say, 10 seconds, and the 10th one takes 100 seconds, your eventual request is going to be delivered to you in 100 seconds, right? So you have to make sure that these stragglers are lifted as much as possible, or they try to deliver as better a performance as they possibly can, right? And again, this is essentially what is kind of shown in these graphs as well. So there is this metric called the 95th percentile or the 99th percentile latency when it comes to sort of distributed services, right? So if you have a large number of requests that are, let's say, being sent over to Facebook for accessing a particular set of photographs, right? So depending on what the network load is and what the load on each one of these servers actually looks like, some of these requests would be met in the kind of the service level agreement that is acceptable to you, right? So if you wanted to look up a Facebook photo and you said a 1 second lookup of that photo from that particular server is acceptable to me, a lot of the people would get their photographs sent to them in a second. But there would be a lot of people who would not get their photograph sent to them in a second, right? Some would take 10, some would take 50, some would take 10,000, right? And what you want to do is take all these stragglers and try to contain them in this particular box over here, right? And again, what I'm going to talk about next is essentially trying to do the same thing, trying to contain all these stragglers into this box, but from a storage perspective, right? I mean, this particular request graph is true for any sort of subsystem that you might look at. It's true for memory, it might be true for caches. What I'm going to take this as an example of is for the storage subsystem. Kind of make sense? Okay. All right. So storage systems of today look something similar to this. You have CPU, you have connected DRAMs, there is an IO bridge, and there are sort of multiple sort of storage devices that are connected to the IO bridge. The actual interfaces might differ a little bit. So the IO bridge, this particular HDD might be connected through a SATA interface. This particular one might be connected through a SAS interface. And I'll show how these interfaces are sort of not being able to cope up with the data deluge that you have, right? There are newer versions of storage devices that are coming up, which I'll also talk about quickly, are the PCIe SSDs. So rather than connecting the SSDs through the typical SATA or SAS interfaces, you would want to connect them over PCIe because, again, PCIe gives you better advantages of higher bandwidth and possibly lower latency as well, right? All right. So this is the subsystem that we are going to sort of concentrate on for the next set of the talk. Quickly go over as to why this is kind of necessary is, so let me Anybody has had any experience with SSDs before, or how the SSD organization looks like? Okay, so to give you a quick analogy, this is very similar to what we have seen for DRAM, right? So if you look at, this is what a typical SSD architecture might look like. You have multiple chips over here, which is essentially similar to the chips that we saw in DRAM, right? So you had 9 chips, 8 had data, 9th one had ECC, and that constituted to form rank, right? And essentially the architecture is very analogous here of SSDs to that of DRAM. So you have multiple chips here, and multiple chips constitute to form essentially a block, right? Then inside each chips you have multiple planes. Inside each plane you have multiple blocks, and inside each block you have small pages, right? The granularity at which you can actually do accesses is that of a page, right? So again, there are the same levels of organization as banks and planes. There are blocks and erase blocks, and let me quickly go over why these sort of notions are necessary. So the way NAND flash works is a little different than how DRAM works, right? In the case of NAND flash organization, you can read at the granularity of a page. So let's say the page in this case is 4 kilobytes. You could read at the granularity of a page, but you can only write at the or you can program at the granularity of a page as well. But before you can program at the granularity of a page, you have to erase the entire block that that page is a part of, right? And that's just because of how NAND flash is actually architected over time, right? So you read at page granularity, which is 4 kilobytes. You program, essentially write at page granularity, which is again 4 kilobytes. But before you can program, you have to erase a block to which that page belongs, which is essentially larger, which is probably 256 kilobytes, right? So that essentially introduces certain delays between reads and writes. All right. Okay. Any questions here? No. All right. Okay. So how does this play into the traditional sort of storage or use of flash as a storage device, right? So people moved to flash because hard disk drives were too slow, right? Hard disk drives have this spinning media, because of which it takes a very long amount of time to access any data. Flash drives don't have any spinning media, and you can look up data from drives pretty quickly, right? So, but the good thing about SSDs, the other good thing about SSDs are that they're inherently parallel, right? So because of the analogy that I gave before between DRAM and SSD, right? So DRAM has this multiple levels of parallelism where you have channels and then you have bank level parallelism as well. Similar is the case with SSDs as well. So you have multiple channels within an SSD, and onto these channels you have these multiple planes that can be looked up in parallel as well, right? So because of this inherent parallelism and this analogy to DRAM as main memory, you could potentially satisfy a whole bunch of requests in parallel from an SSD that were not possible before from a hard disk drive. So that is one good thing about SSDs. The second thing is that the NAND technology, the NAND flash technology itself, has been progressing very well over time, right? In terms of storage density, it has been doing well. There is something called 3D VNAND, which is here, which essentially is very analogous to 3D stacked DRAM, right? So you rather than going sort of vertical, you go, rather than going horizontal, you go vertical and try and stack as many NAND devices as possible. So again, storage densities are going up, which essentially means that the raw device performance keeps on scaling, right? So if I have multiple channels within an SSD, the amount of data that I can look up within an SSD itself is very, very large, right? So I could potentially look up, or I could potentially get 6 to 8 gigabytes of data lookup within an SSD at any given point in time. The problem with SSDs before PCIe came into picture was the fact that the SSDs were essentially connected to the system using traditional interfaces, which is either SATA or SAS, right? SATA or SAS as an interface itself is pretty slow. So it can only deliver up to 6 gigabits per second to the system itself, right? So the reason why SSDs used these interfaces, by the way, can anybody guess why would, so if I have a device that is inherently super good, but I'm connecting that to my system using an interface that's not so good, any reason why would I want to do that? Sorry? Sort of. Well, okay. The reason is because it's there, right? SATA interfaces exist, SAS interfaces exist. It leads to easier adoption, right? So if I develop an SSD that talks to the system using SATA or SAS, I can just sell the SSD, people can plug it in, and it would be usable right away, right? At some point in time, the internal sort of bandwidth and latency that can be provided by an SSD would not be matched up by this interface, right? And that's the point where you have to switch interfaces, and that's why you go from SATA or SAS, which was the interface of choice for a traditional hard disk drive, to something which is PCIe, which has much higher bandwidth and much lower latency, right? So again, this is essentially what this particular sort of cartoon is showing. So if you look here, right, if you have 40 lanes of PCIe Gen 3, which can provide you up to 320 gigabits per second, right? So in this case, you can have a lot of sort of parallel flash devices that can potentially be connected to the system, which can give you a lot of bandwidth, essentially, right? Any questions here? Okay. All right. So the problem here was that up until I think 5 years ago, Fusion IO was the first company to put PCIe connected flash onto the market, right? So their innovation was pretty simple. We have PCIe that exists, we have flash that exists, we are just going to build a device that connects or acts as a block device and connects over PCIe. Pretty simple. The problem was it was not standardized. So they had their own sort of hardware logic that was sitting somewhere over here, and it was proprietary, right? So if you wanted to talk to the CPU, or this device wanted to talk to the CPU as a storage device, it had to go through the proprietary Fusion IO logic, which only they could sell, right? So at some point in time, the industry decided, well, okay, it's time for us to standardize this thing. You can't just have one sort of an entity controlling the entire market, right? So in order to do that, what they decided to do was come up with an interface for a storage device that sits on the PCIe, but has a standard interface of talking to the rest of the system. What that interface was essentially called was the non-volatile memory express interface. So it's a software-defined interface that is built on top of PCIe that lets any sort of device act or talk to the system and behave as a storage device, right? So what it does at this point in time is essentially tries to utilize the parallelism that's offered by the flash devices themselves. So I talked about how flash inherently is parallel within it, and how that parallelism was not being exploited enough by the SATA and the SAS interfaces. So what this particular protocol tries to do is try to build up software standards that have sort of multiple of these parallelisms, right? So they have these things called the submission queues and the completion queues, and these things exist in pairs. So anytime you have, and you can have a whole lot of these pairs. So think about having 64,000 of these submission and completion pairs. Anytime an IO request comes in, it goes into one of these submission queues. And anytime the device completes the request, it's sent into this completion queue, right? And since you have multiple of these around, you could potentially use the parallelism that's exported by the SSD and try to make the most of it, right? The other good thing about NVMe is the fact that it's independent of what kind of memory technology you have here, right? So today it's flash. Today it's flash that is the predominant memory technology for storage devices. Tomorrow it could be 3D crosspoint. The day after it could be STT-RAM. The good thing is this protocol doesn't care. It could be anything. As and when you keep bringing in better memory technologies to the device, this would still keep on scaling very well. because you can keep on increasing the number of submission and completion queue pairs that you potentially might have. All right, make sense? Okay. All right, so because of the inbuilt features of the protocol itself, and because of the fact that it's built on PCIe and it's a software-based interface, it's able to provide you all these very nice things, which is lower latency, higher bandwidth, latency consistency. This is something that sort of relates back to the stragglers that I was talking about, right? In SSDs, because of the things, because of the way things are architected, there is this concept of garbage collection that happens in the background every once in a while, and because of this garbage collection, you potentially sometimes might get very high access latencies, sometimes pretty closer to what hard disk drive might export as well, right? So because there is enough parallelism in the system, you get a much better latency consistency, as in you contain the number of stragglers that you have in the system. And again, you get some power benefits as well. This is not strictly true though. All right. Okay. So some of the work that we published when a couple of years back when I was still with Samsung was essentially trying to characterize where the benefit of these devices is actually coming from, right? So I talked about the fact that it has parallelism. I talked about the fact that it has software, sort of a protocol that sits on top of PCIe, right? So we are trying to characterize, well, okay, there are these multiple innovations that are going on. So where is the benefit of this particular thing coming from, really? Right, so what we did was essentially we compared SATA hard disk drive, which was sort of the best in case enterprise hard disk drive, 15K RPM. Then there was again an SSD connected to the SATA interface, and then the third point of comparison was an NVMe SSD, which was again connected to the system using PCIe. All right, all these experiments were done on an 8-core Xeon E5 2690. Anyways, some raw numbers here, and again, these are all actual measurements on actual machines. 3 different kind of devices. The x-axis in this particular graph is bandwidth, and in this particular case, the devices, and the IOPS, which is input-output operations per second. So as you can see, hard drives are pretty terrible in terms of random reads, right? So if you have random reads, it's 190 random reads, random IO operations per second, whereas in the case of NVMe, it was around 750K. In terms of sequential read bandwidth, again, hard disk drives did a little better because again, they do well on sequential workloads, but again, the NVMe drives did way better. So 3 gigabytes per second is pretty much as close to the interface bandwidth that you can get, right? So the point of putting up these numbers was the fact that you can build a system that that can deliver performance as close to the interface as possible, right? In this case, again, this one was particularly limited by the interface itself, right? So the internal architecture of, as far as the layout of the flash is concerned, is not very different probably here and here, but a lot of the difference in performance comes from the fact that now you are on a completely different interface. Okay, a little bit of latency comparison here as well. So when we are trying to look at unloaded latency, it's essentially there is one thread that's sending out one request, and we are trying to measure the round trip time of that one request, right? So there is no other load in the system as well. So again, what you would expect is these two numbers for the SATA and the NVMe sort of look very, very similar, right? Again, because this is unloaded. The difference comes when you actually have a large load. So when you have a high load, essentially you have multiple threads that are sending out IO requests in parallel to these multiple devices, and that's where essentially this particular type of device starts to shine, because it has that inherent parallelism in terms of submission and completion queues that I talked about before. And as you can see, that 99th percentile latency, which is essentially the amount of time in which 99.9 percentile of your requests are completed in. So if, let's say, this number was 500 microseconds, that essentially means all the IO requests that were sent out, 99.9% of them were completed in 500 microseconds or less. In this case, it's particularly higher, sort of twice that value, right? So again, you get benefits in terms of latency. Again, raw performance comparisons. Okay, the stuff that I was talking about, how much time do I have? 15 minutes? Okay. All right. So the other kind of things that I was talking about before was trying to characterize where in the system software. So if you have an NVMe device, that essentially means it is going through some sort of a different stack in the OS as well, right? And is there some benefit to doing that as well, right? So okay, before we go there, in a traditional IO device, what happens is you have an application which, if it wants to do an IO call, it goes through the system call interface, then which calls the file system. Then you have the page cache, which is essentially a cache of the previous IO operations sitting in the memory. You could potentially go through a device mapper as well, but usually you go from the file system to the page cache to the block layer to the particular device driver, right? And this device driver could be for a hard disk drive, for SSD, whatever that might be, right? What had happened in the case of devices that were still sitting on the SATA interface was this stack has essentially been optimized very, very heavily for hard disk drives, right? People knew that hard disk drives are or do well on sequential access. So this entire stack has been optimized super well for hard disk drives. The one thing that people also hadn't thought about before was the fact that there are all these different layers that a particular IO operation has to go through before it actually gets to the device over here. There are multiple bottlenecks. If you have to go through multiple layers, that essentially means there could potentially be multiple bottlenecks in the system as well, right? And the couple of things that we sort of figured out was the fact that the block layer itself was sort of the biggest bottleneck, and this was published by a group from, I think, the Netherlands in Sisto 2015, and they sort of, or we verified what they had found out before, was the fact that if you have devices that are super fast, the block layer becomes a bottleneck because there are only the amount of parallelism in terms of IO queues that's present in this particular layer is very, very small, right? And again, that will sort of become a little more clearer here, I hope. So on the y-axis, you have the amount of time. So if I have an IO request, what is the amount of time that I actually spend in the software as opposed to the hardware, right? So I have an IO request that is generated by the application. It goes to the stack of the OS, then it goes to the device, and then comes back up, right? So there's some amount of time that's actually spent in the stack. And what we tried to figure out was, has that decreased when we increase the, or when we go to a different interface, which is NVMe, which is software based, as well as exports a lot of parallelism, right? And we found out that indeed that was actually true. So a SATA SSD spent around, I think, like 28% of the time in software, and these are the various sort of places that it spent its time in, which is kernel, block layer, application, and whatnot. And in the NVMe SSD, as you can see, the amount of time that's spent in the kernel goes down a whole lot, and there is some time being spent in the driver. And again, this is mostly because of the fact that there are these multiple sort of submission and completion queues that are there, which are able to process things much faster. All right. The other thing was, in this case, the yellow bar, which is the time spent in the block layer, sort of goes down as well, because the NVMe devices that we actually characterized sort of bypassed the block layer. The small overhead that sort of is in there is because they were not actually processing anything in the block layer, but they still had to make the function call, so there was a little bit of an overhead there. But in this case, all the IO requests had to actually go through the block layer, as well as spend some time there because of that single submission queue that was present there. All right. Okay, so we did some more performance in terms of performance comparisons in terms of typical data center workloads. You have a TPC-C, which is an OLTP workload. Then we did some performances with or performance characterizations with NoSQL databases, Cassandra, MongoDB, and okay, this is something which is interesting, right? So if I what I'm going to compare the performance of is one SSD versus four SSDs. One SSD is on the SATA interface, four SSDs on the SATA interface, and there is one NVMe device which is again on the PCIe interface, right? What this shows here, the amount of green, so this is time, as the application progresses. This is the amount of CPU utilization on the y-axis, right? The higher the green component there is, that essentially means the application is waiting for the I/O to complete, right? So you would want this green component to be as low as possible. If there was a blue or a red component, that essentially means the application was doing some actual work. Green components means it's just sitting there waiting for the I/O to complete, right? So as we go from 1 SSD to 4 SSDs, 4 SSDs were in a RAID 0 combination, so it is sort of striped across the 4 SSDs. So you can see there is a decrease in the amount of weight that's there, and again that's because there is an increase in parallelism in these SSDs. But you go from 4 SSDs to an NVMe device which has even increased amount of parallelism at the level of the software interface itself. So you can see there is almost no weight in terms of CPU time, and all the work that's actually being done is essentially useful work, right? So blue is time spent in the user mode, red is time spent in the kernel mode, and that's where the actual work really happens. All right. Okay. Another 5 minutes, 10 minutes. Okay. All right. Again, I have some more numbers over here for Cassandra is another sort of NoSQL database that we characterize with. The numbers are pretty much in line. The one thing that we found very interesting was something called MongoDB. And again, we are surprised to find that there were almost no performance improvements over here. So essentially this is 1 SSD, these are 4 SSDs, and this is 1 NVMe drive, right? So we are expecting performance improvement similar to what we had seen before, but in almost all of these cases, there was negligible benefit going from 4 SSDs to 1 SSD. And it turns out it was not a function of the device or the interface or the protocol itself, but it was the difference was in terms of how MongoDB does stuff internally, right? So MongoDB, when it tries to sort of do memory accesses, it just maps a whole bunch of stuff. And it turned out that what we had in our system was around 128 gigabytes of main memory. So when it tried to mmap, it just mapped everything, and everything in most cases was just coming out of DRAM, right? So when it's coming out of DRAM, there is essentially just no difference whether you have 4 SSDs or 15 SSDs or 1 SSD compared to 4 good ones or 4 bad ones rather. So that was sort of interesting, right? So again, move from SATA to NVMe has definitely its advantages. There are advantages to moving to a different interface, just because a new interface is able to utilize the internal capacity of the storage device in a much better fashion than before, right? And again, this has a lot of potential for improvement everywhere else as well. So one thing that I really quickly want to talk about is, so NVMe in this case that we are sort of talking about was direct attached storage, right? So you have a server that has direct attached storage over PCIe, which is the NVMe device that I was talking about. What it turned out in the case of micro benchmarks, I showed some results where there were micro benchmarks that were sort of utilizing the entire PCIe bandwidth, right? But when you turn to actual applications, the latency consistency was there, but we're not able to push the bandwidth as much as the interface was allowing us to do, right? So one of the things that people have been exploring is, rather than having this NVMe device attached to one single server, right, where it is just being able to be used by that server that it's directly attached to, what you can do there is potentially try and have these NVMe devices attached to a bunch of servers, if that's possible, right? So what it essentially needs to do is these devices have to be able to understand this NVMe protocol, but over the network, right? So rather than putting this NVMe device in one server, I want to put a bunch of NVMe devices in one server and make that server sort of shared across a whole rack of machines, for example. So in that case, that is essentially what is called NVMe over fabric, or NVMF. And the reason why that's essentially becoming possible is because how networks are progressing very well as well, right? So up until now, high speed, low latency networks have been sort of the domain of HPC people. Very, very expensive networks that were built into these supercomputers. That's not very true anymore, right? The way commodity network, the trajectory that commodity network has been taking over the past few years is essentially 10 gigabit per second Ethernet is very common, 25 is being deployed, 40 is being deployed, 100 is around the corner, right? So you can have networks, commodity networks that can deliver up to 100 gigabits per second, which essentially sort of matches up to a bandwidth of 4 or 5 of these SSDs, right? So because of these developments in the SSD technology or the storage technology, as well as sort of parallel developments in the networking domain as well, would enable us to create these sort of massive storage devices over the network, which are high capacity, high bandwidth, and low latency, right? And essentially that's sort of what's being showed here. So this one shows how the link speed of different networks has been increasing over time. So it says somewhere around 2018 is when 400 gigabit Ethernet, 400 gigabits per second is essentially going to become mainstream, right? And utilizing this, we sort of tried to build network designs or storage designs that are essentially low latency, high bandwidth, but across the network, right? Again, so let me just see if I can bring up a picture of that. Right, so you have a whole bunch of these servers that are over there. You have this high-speed networking that I was talking about before, and you have a JBOF, which is essentially just a bunch of flash or high-speed NVMe devices over there. So the idea is, because this is shared storage now, each one of these guys can access any one of these devices over here. So you don't need to plug in a very costly and a very high performance storage device into each one of these servers. And it scales very well as long as your network and your flash devices are able to sort of keep up with that as well, right? So the idea here is that let me just go back to this example. All these devices over here should be able to understand the NVMe protocol as well, right? So when I talked about NVMe before, I said this is a software protocol built on top of PCIe, right? Now, can I take that exact same protocol and build that on top of Ethernet? If I can do that, this essentially becomes a reality, right? And that is essentially what a lot of people are doing. NVMe, I think, is either standardized or very close to being standardized right now, which essentially means some application over here can send an NVMe request across this Ethernet fabric to a device over here, which was not sort of possible before, right? And this is sort of the proof of concept thing that we built a little while ago, not here, when I was still at Samsung. The idea was you have this fast Ethernet, you have a whole bunch of remote storage over here, you have a sort of clients that are connected to this application server. So you have the application server which is running your database or whatever have you. It doesn't have any local storage, right? All the storage that it has is over the network in the form of these sort of PCIe devices over here. And the idea was to see how this compares with if I take this NVMe device and connect to this server over here, right? So the idea is this case and this case should be pretty similar in performance, if that is possible, right? And let me just quickly go through the results over there. Right, this one, right? So some of the results that we did, and again, the workloads that we used were again Cassandra in this case. So Cassandra was driven by a couple of YCSB workloads. So DAS in this case is direct attached storage. Underscore A essentially means direct attached storage, which was running workload A for YCSB. NVMe is remote storage, again running workload A, direct attached running workload D, and NVMe running workload D, right? So again, as we scale the number of instances of the database that we're running on a particular server, we see that, again, the remote and the local performance sort of keeps up really, really well, right? The other thing that was interesting in this scale was essentially the tail latency. Remember I talked about 99 percentile latencies before? In this particular case, both, so this is NVMe and this is NVMe, right? So again, both the tail latencies were also very contained or very similar to what you would see on a direct attached storage device as well, right? So the idea here is that you were able to get tail latencies that were very similar to direct attached storage devices. Again, and because I'm running out of time, just try to give you a quick idea as to what all can be done in this domain, right? So again, in terms of when you look at the industry side of things, everything is about consolidation. If you pay money for something, you have to be able to use it as much as possible, right? So it's all about consolidation, which in terms of storage translates into something like this, right? So if I have a rack of machines, rather than putting in expensive storage in each one of these sort of machines, I would rather create this one big box over here and put all my nice storage in that box, and then connect all of these machines to that nice box over there using some high-speed network, right? Now, if I'm able to do that, then it becomes another problem of how do I change the design of this node now, because this node doesn't have to have a lot of storage capabilities, right? It only needs to have a lot of compute because all the storage is down here. So that becomes a very interesting problem to think about as to how the architecture of this compute node is going to change in assuming that this is going to become a reality, couple of years from now. And then again, the other thing that's been coming up is essentially the use of containers to sort of distribute jobs across all of these machines. So are there ways to sort of distribute jobs across these different compute nodes so that you can, reduce your tail latencies even more? You can sort of maximally utilize the available bandwidth and sort of get the best performance out of all of these different nodes, right? So, all right, with that, I will take any questions if you have. Okay. All right, thank you very much.